Hi everyone, this is Jiahui Huang. I will present our paper entitled A Neural Galerkin Solver for Accurate Surface Reconstruction. This is a joint work with Hao-Xiang Chen and my advisor Shi-Min. Our task of surface reconstruction aims at building a 3D geometry that respects the input in the form of point clouds. We specifically represent the geometry using the implicit field, from which triangular mesh could be easily extracted. One major work in this line is called occupancy networks, where a multi-layer perceptron is used to parameterize the implicit field, and the shape could be controlled by latent vectors. While they could learn a semantically meaningful distribution for the shape collection in high level, the recovered shape usually cannot faithfully respect the input point conditions. On the other hand, another renowned work called Screened Poisson Surface Reconstruction, or SPSR, solves for a Poisson system that explicitly treats the input points and their normal as data constraints, and is hence very accurate if the points are noise-free. However, in presence of extreme noise or incompleteness, which are commonly seen in real-world scans, because their regularizations are actually handcrafted and there's no data priors exploited, such a method usually fails to produce smooth and nice results. The above dilemma motivates our approach. So we want to combine the best of the two worlds by building a method that can not only leverage data priors that induce high-level semantics to gain robustness towards noise and variance sparsity, but also satisfy low-level data constraints available from the raw input data. Additionally, the method has to be scalable to large scenes, which allows for practical use. To build our method, we will first introduce a very related work, Screened Poisson Surface Reconstruction, by Michael Kochtan in 2013. The method starts with a simple observation that if you take the derivative of the smoothed occupancy function of a shape, you will get a normal field whose samples should include the input-oriented points. Hence, by taking the inverse process, you could basically recover the geometry of the input point. Such an inverse process is achieved by solving Poisson equation, derived by applying the variational method to the following energy equation EF to obtain the best implicit function F. In order to make the function respect the raw information from the points, SPSR further adds positional constraints into the energy formulation so that F is encouraged to evaluate to the target scalar value xi that represents the level set. The function f is discretized using finite element method as a summation of basis functions defined on the voxel-savant tree. Using such a discretization, minimizing the function EF boils down to solving a linear equation L alpha equals D in closed form. The solution alpha serves as the coefficients of the basis functions by scaling them to fit the normal and positional constraints. How does the two constraints affect the final solution? From careful inspections, we have the following key observations. First, the normal constraints are important because it drives the sign of the implicit function. However, even if they are not 100% accurate, say several degrees of the ground truth values, they still serve as an important orientational guidance that effectively regularizes the geometry. Second, the positional constraints are, admittedly equally important because they sample the surface locations and help determine the correct level set to extract surface from. Given the above observations, we hereby answer the question that, with the availability of large-scale training corpus, how can we incorporate inductive bias learned from the data into the reconstruction process? For normal, this is not hard. There are already many normal estimators for 3D point cloud data from the literature using the power of deep networks. How about the closed form solver? How do we actually incorporate useful data priors into the solving process to make the solution more robust? To this end, we propose to use learnable basis functions to discretize the solution space of the implicit function. In comparison to the fixed Bezier tensor basis used in SPSR, we propose a spatially variant definition of the basis functions. independently defined for each voxel in each octree hierarchy. So specifically, we parameterize the basis as a summation of elementary functions. These elementary functions include polynomials and trigonometric functions that reflects high-frequency details. They are later added using the learned coefficients that are predicted by the network. As shown in the figures on the right, using spatially varying basis functions enable a larger solution space for the implicit function, leading to geometries with better qualities and vast amount of details, while keeping the voxel sizes unchanged. Our full pipeline hence goes as follows. Given input point cloud, we first feed it through an adaptive sparse convolutional neural network. Such a network actually resembles a CNN backbone with encoder, decoder, and skip connections, but with sparse voxels processed by sparse convolutions. Moreover, in the decoder, a structure prediction branch is added after each layer to predict the existence of finer level voxels. This allows us to build a multi-scale voxel grid whose joint domain forms the solution space of the surface fitting solver. The features stored on the voxel grids as regressed by the UNet are used to compute useful attributes. For each voxel, we predict the coefficients of the basis functions and the normal data. For each input point, we further obtain the trilinearly interpolated feature from the feature grid and pass them through an MLP to obtain the target scalar psi, defining the expected value at that position for denoising purpose. With all the attributes in hand, we plug all of them into the surface fitting solver. Similar to SPSR, we also solve for a screened Poisson equation, but using network predicted basis functions, as well as normal information. This helps effectively incorporate data priors into the solver. As our basis functions have local support and the voxels are sparsely allocated in space, the linear system we build is also a sparse one, allowing for efficient GPU solvers to be applied. We further use a coarse-defined scheme similar to the multi-grid technique to further reduce the complexity. The final implicit field can be obtained by multiplying the solution alpha with the predicted basis function in a spatially varying manner. Dual matching cubes could be used later to extract the meshes whenever necessary at arbitrary resolution. We validate our method on various different datasets, and one of them is ShapeNet. In comparison to all of the baselines, we can reach outperforming reconstructions even when the input is very sparse and noisy. Compared to man-made objects, human bodies' geometries exhibit finer details that are more challenging to recover. To demonstrate our applicability, we utilize DFIL's dataset. As visualized in this video, our method used inferred priors from the networks are effectively merged into the solver. We are hence able to recover more details. The scalability of our method is further tested using Matterport 3D dataset. Our method performs favorably over all the baselines, introducing nice and smooth complete room-level reconstructions with abundant geometric details. In comparison to overfitting-based methods like Siren and Acorn, because we actually use a closed-form Euler-Lagrange formulation that requires only a linear solve, our method is actually reconstructing scenes both fast and accurately. We also tested on Kitty dataset using chunks. Notably, the use of our multi-scale grid allows for adaptive mesh extraction, which significantly saves computation power. Despite the promising performance shown above, our method admittedly suffers from the following limitations. First, the time and memory cost of the solver is still high. Second, transformation equivariance is not guaranteed in the regress attribute from the network. Third, the method could not be trivially adapted to shape completion tasks due to our heavy reliance on the raw input point cloud data. We wish to further tackle these limitations in the future work. Thank you for listening. Due to the well-known regulations of the government, we are very sorry for not being able to do the presentation in person, but I will be online in a Zoom conference during the Q&A session, and I'm happy to take questions. Thanks.